Okay. Uh, Thank you all sorry about, I know you've all been in the waiting room for a long time. I know it's late in the period. I apologize. Good afternoon. Yes. All right. I'll explain why. Thank you for indulging and tolerating my lateness. I apologize. I'll explain in a second. I'm just looking in the chat. So hello to everybody. Who do we got here? All right. Oh, awesome. All right. So good afternoon, Kaya. Good afternoon, Yaneli. Good afternoon, Gabriella. Good afternoon, Ariana. Good afternoon, Erica. Good afternoon, Roger. Good afternoon, Genesis. Good afternoon, Sydney. Good afternoon, Emanuela. Good afternoon, Brandon. Good afternoon, Samantha. Good afternoon, Alfred. Good afternoon, all. Okay. So bear with me for a second. Oh, and more people are, who's that? Okay. Bear with me for a second. Um, Hold on. Yeah, obviously off to a slightly rocky start here, or I am. What is going on? Wait, I'm a little concerned. Hang on. Wait a minute. Okay, okay, okay. Um, so here, oh, something in the chat. Yes, good afternoon, direct chat person. Thank you. Okay, we're starting 10 minutes late, and that's totally my fault. I'll tell you why we started late, because the first order of business is that the exams were due at the beginning of class for this class, and they were due at the beginning of class for the last section as well. And I think that was pretty clear. So first, let me say that those of you who have turned in your exams, congratulations. That is awesome. Seriously. Um, if you are done with your exam, you may have found that it was a slightly more intense experience than maybe it seemed like it would be. So if you have turned in your exam as was expected, you should congratulate yourself. You should be proud of yourself. I would imagine it took a little bit of work and a little bit of sweat, and good for you for being done. And furthermore, let me say, it sounds like I'm angry. I'm just a little catching up with myself here. But first of all, if you are in the room right now and you've turned in your exam, which was the expected thing to do, then also congratulations for sitting here and being here. You probably are exhausted and you probably don't want to be here, but you are. So thank you. And it's very noted, like specifically on exam days. Believe me, I know who's here and who's not. So thank you. B, even if you are worried about your grade, or even if you are worried about how well you did on the exam, a couple things to say about that. Number one, you congratulate yourself twice, because now the ball is in my court. You did the right thing. Until you hear otherwise, you did an amazingly hard thing. And you did it well until you hear otherwise. And you probably did do well. So don't give yourself a moment to congratulate yourself on the fact you that you completed the task. And maybe you even made the hard choice of saying, I could make this better, but I'd rather just get it in on time. That was the right choice. So before you move on to worrying about the grade, just breathe out and pat yourself on the back that the ball's in my court now. And if I got hit by a truck, I shouldn't say that, but if suddenly everything fell apart and I couldn't grade these exams at all, you would do well, not badly. If that makes sense. I mean, the benefit, like the tie goes to the runner. So, so please congratulate yourself on being done for the moment. Second of all, no, I will move as fast and hard as I can. Um, but it will take me a while to get these back. You're not going to have them this Wednesday. I can assure you of that. And I apologize, but they are way too long and too big and too many of them. Also, as you know, I do have chemo this Wednesday. I won't be here. You'll have Professor Liu. What you'll do with Professor Liu is move on through with the new material of Newton's laws and the homework that is due on Wednesday. So again, now I'm still not finished with this little speech here, but what your next task is to start working on homework 8, which is Newton's laws. It's on new material that we're just starting today. So a lot of it, so it's long, a lot of it is hard. Your job is just like with the exam, turn in something, turn in a first draft of homework 8 on time for Wednesday. And as long as you turn in something substantial, that's a first draft, even if it is not complete or certainly not correct, you will still have time to revise and upload and get all the remaining points as long as you turn in something on time for Wednesday. And then you can ask Professor Lou, or Professor Lou will be, dealing with it so you can get more clarification stuff from her and then from me on Monday, etc. So stay on the path and just do something authentic for Wednesday. I won't be here and I will be in chemo and all kinds of things all week. So it'll take me a little while on the exams. And again, that's an advance apology, but bear with me. Or I thank you in advance for your indulgence. Now, on the other hand, if you're in the room now and you haven't turned in an exam yet, this is a little of a trickier point. If you're in the room now and you haven't turned in an exam, hopefully you made some kind of prior arrangement with me. Hopefully you reached out to me, and some people did, and you alerted me like, oh, I thought everything would be fine, but it's not. I'm getting squeezed. I might need a little more time on this. If you made some kind of arrangement with me, still, as you all know, there still will be some point deduction, but it'll be reasonable and moderated and minimized if there was, to the extent that there was communication with me. If you're in the room now and you didn't turn in your exam yet, and it appears that that is some of you, and you didn't make an arrangement with me, like you didn't alert me at all before. So here's the deal to say to everybody, because our final exam arrangement will be very similar to this one, and same thing in Physics 204. So this is the first time we've had this experience together. Let me be clear. If you didn't turn in your exam yet, and you didn't alert me at all of that fact, there's two pieces of news to give you. One is that is not what you want to do in the future. That's not the right move. If for whatever reason you couldn't turn your exam in on time today, the best thing you could have done, or I'm telling you for the future, I think I did tell you this, but the best thing you could do is, even if it were 10 minutes before class, send me an email saying, acknowledging that that I know that there's a situation. And even if it's 10 minutes before class where there's nothing that can be done about it, at least you've then shown up to class with a somewhat of a clear conscience, or a clearer conscience, and a recognition to me. Like, in other words, you're not running away from the situation, right? So in the future, if somehow you can't get the exam in on time and you're making the choice, is it even worth me telling him at this point? Or am I going to bother him? Or is he even going to check his email? And by the way, some of you might have sent me an email 10 minutes before class. And I'm right, I haven't checked it because I was in the other class, but I'll still see when it was sent, right? You would prefer in the future to have a communication on record that at least acknowledges that you know what the deadline was and this is not ideal. You will still lose some points. Anybody who's late, you will, but I will take the exam, and I'm still going to take everybody's exams. Let's get this clear to everybody for the final exam. I will take your exam, but if it's late, there's some points lost. How many points are lost? It totally depends on how you manage the situation. Really, it depends on how much honesty and communication there is. So in the future, if you want to try to minimize the damage to yourself or the situation between us, communication is always better than not. Even if it's 10 minutes, of course, 2 days is better than 10 minutes, but 10 minutes is better than none. Okay, so that's just for now. If you're still in the situation here where you didn't communicate at all and your exam, am I still going to take your exam? Yes. And am I going to destroy you with a point penalty? No. Like, am I going to turn it like you would have gotten an A, but you're going to get an F? No, nothing like that. Okay. But if you did, and if you did, and I'm going to move off this topic in a second, but one of the reasons I was late coming to this class is there were a couple of people in the other class that were in that situation that didn't turn an exam, never told me in advance, not ideal. But they came to class, and each one of them individually I spoke with afterwards so we can figure out what to do, what's going to happen, and how I will still take an exam when they turn it in, but there will be consequences, blah, blah, blah. And so those of you, I'm not trying to shame anybody. I'm just trying to be clear. If you're in the room now, and I'm also trying to make it clear that you're not sunk. It's not a disaster. It's just not ideal. And the ideal thing in life is to try to take non-ideal situations and make sure they don't become disasters. So that goes both ways between you and me. If you're in the room right now and you did the exam and you're here, then congratulations and awesome. Okay. And I'll move on in a minute and you should be breathing. Those of you who still owe me something, eh, like an exam and communication, I would like you to give me the communication right after class. I'll make breakout rooms. I'll be quick. I know you have somewhere to go, so do I. But I'd like you to hang out and just so we can touch base for a minute and clear the air. And then we can both move on as dignified human beings who are not in a doghouse or are not ashamed of ourselves or are not angry or anything like that. I.e., the point consequence will take care of that. There will be a moderate but differing case to case point consequence. Then we'll know that. That's like the cost of doing business. And then we move on and respect each other mutually after that. Like for real. So hang out, please, after class if you still owe me an exam, and particularly if you owe me communication, and we'll work it out. And then we'll be friends again, or whatever. We'll be whatever we were before. And I mean that. Lastly, to end on a positive note of this, again, if you already did your exam, I'm not talking to you, and you should be proud of yourself. But I want to say also, and I mean this, even though it sounds like I'm being all something. If you didn't give me an exam yet, and you didn't give me communication, but you're sitting here in this class right now, and you're tolerating this little speech, you should be proud of yourself. You should be proud of yourself. And I'm noting it. I know who you are. Like I know which exams are in and which are not, obviously. And if you're sitting if you came to class, even knowing that you weren't totally on the right page, if you didn't finish the exam, but you came to class like I asked, you should be proud of yourself. And I am noticing it, really, because it takes courage to do that, to face the music when you're off beat for a moment. If you did not turn in your exam, the note I want to end on right now is if you did not turn in an exam and you didn't communicate to me like a special circumstance, then you're going to hang out for 2 minutes after class so that we can just make a human, dignified arrangement with each other and we can move on in our lives. And I want you to know before you hang out after class, I'm proud of you for making the tough decision to show up even when you're a little bit like empty-handed for whatever reason. I want you all to know I was a physics major in college. I also had another major, but I was a physics major in college and I went to graduate school twice for physics. I want you to know that is not because I found physics exams easy or an easy experience. It took a lot of courage for me sometimes just to show up for a freaking exam or the day after exam. And believe me, there were exams that I failed. Believe me. And there were days I just didn't want to show up or face the professor at all. Believe me. And I know that some of the hardest things to do, harder than a physics problem sometimes, is even just like showing up with a professor. So if you're here today and you didn't perfectly do the right thing, but you showed up anyway, you did a very good, very right decision. And you probably were wondering whether it was the right decision. I would imagine it was the right decision, and it will be taken into account when we figure out what to do next. And I'm even going to add to that too, when we meet briefly after class, each one of you, whoever I'm talking to right now, first of all, I'll be aware and you'll be aware. There are some people that are even worse off than you because they didn't even show up today. Believe me, like it is okay, there's always someone doing better. Don't worry about them. And there's always someone doing worse. Don't worry about them. But believe me, no one's situation is perfect or perfectly unmanageable. When you show up after class to talk to me, show video. That would be a good move. I mean, so I can get to know you better. Okay. Anyway, that's enough about that. I just want everybody to know physics is hard. Physics classes are hard. And my exams in college were take home as well. And at first, when I had taken exams, I was like, this is such a gift. And it turns out they're like stressful in a totally different way, aren't they? They're surprisingly stressful in a way because you have nowhere to run, but there's like no one between you and you when you sit down. And that's scary. And there's no one to blame. But anyway, I know it. So I'm here to ultimately be so nobody, no matter what your situation is, no one, if you're listening to me right now, you've not failed this class and you've not given up on your chance to pass this class or even do well in this class. The show is not over for anybody. This was our first exam of four, if you stay with me for the next semester as well, right? So it is ultimately about challenge and compassion. I promise, no matter how I sound right now. So that said, I hope that's all clear. Anyway, that said, I'll just say this clearly too, in case it's not clear. It's still the case that I have no limit on how many good grades will be given in this class. I have no limit on how many people will pass this class. I want you to succeed. I hope that's clear. Like my interest is in your success and in you helping each other. That's it. So I want that means in many people getting better and better with everything, exam management, whatever. All right. Anyway, so we're going to move to class material now. I'm here to start you on the new topic, which will then be continued with Professor Liu on Wednesday when I'm gone. Then I'll see you again next Monday, unless there's some holiday I'm forgetting about. We're moving to the new material now. You can stop me at any time. And I know we're already like this is meant to now be a relax. Now relax, please, whoever you are. Where just like relax and try to absorb this new material. It's going to be okay, no matter who you are. And I just said the hardest things I have to say to whomever. So it's not going to get harder here if you meet me with me after class. But so new material now. We're totally moving now to Newton's laws. Okay. If you have any question at any time about what I'm about to say, please do put it in the chat. It turned out to be very discussion oriented in the last class because everybody was breathing out, and that's great. I don't want to solve a million problems today. I'm not going to do a bunch of math. We're trying to understand three laws that you've heard before in your life, like in high school. I'm sure you've heard these laws. Now we're trying to make them more concrete and usable for problem solving at a college physics level. So the idea is to absorb this material and try to get your head into a new place with some laws that you've heard before. So any questions you have, put them in the chat, please. Or if I still haven't addressed some concern or something about grades or exams, you can put that in the chat too. But that said, sorry, okay. So clean slate. What you see on the board here is a little glimpse or foreshadow of the three laws of Newton that we're going to discuss today. But first, I'm going to lay out as three laws. The sort of foreshadow or spoiler alert is that you're going to see that the first law of Newton's first law of motion, what it really is the now sixth form of Galileo's principle of relativity. And the third law of Newton is really the seventh form of Galileo's principle of relativity. And the middle law, the second law, is, I would argue, is not actually what the middle law is the mathematical encapsulation of those concepts and the mathematical formulation that we directly and explicitly use when we solve problems from here on in physics, like forever in physics. The second law is the mathematical underpinnings of problem solving for the rest of physics. And the other two laws are the English or conceptual background of that math. So here we go. Okay, so sorry. Okay, so Newton, couple of things. Galileo lives and work. If Galileo is the grandfather of classical physics, then Newton is the father, so to speak, of classical physics. Galileo lived and worked in what we now call Italy, and he died in like March or so of 1642 AD, CE. Newton's birth is actually sort of historically controversial. Like the records differ, and we sort of changed the calendar was sort of changed at that time in a way that makes the date sort of confusing. But basically, according to some accounts, Newton was born on Christmas of 1642. On other accounts, he's born more like New Year's of 1643. I prefer to believe the former, I love the idea that Newton was born essentially at the end of the same year that Galileo died. Either way, the point is Galileo lived and then died, and then Newton lived. So they never met or anything like it's two totally different countries. But Newton was well aware of Galileo's work. And Newton produced a lot of work. His main huge work was this enormous book that covers a lot of ground called the Principia Mathematica. This is where, as you may be aware, Newton essentially in one part of his mind invents or discovers what we now know as differential calculus. And in the other part of his mind is establishing all these laws of physics. Remember, Galileo's original principle of relativity says the laws of physics remain the same at all constant velocities or in all inertial reference frames. Galileo's principle is a statement about how the laws of physics will work regardless of what they are or might ever be, right? Galileo lays down the formulation that essentially says how laws will operate in physics. And then it's Newton that comes along and actually makes the laws. Like we don't actually have Galileo's law of motion, we have Galileo's principle. Newton picks up on this principle and starts establishing laws of motion. So the first one is here on this first page, but you can barely read it. I can see that. Excuse me. Well, I'll read it out loud, but then there's a clear version on the next page if you're stressing to get the handwriting down. I'll show you the next slide in a second. But what it does say in English, Newton's first law of motion is, unless acted on by a net external force, an object at rest stays at rest. I'll try to make this. An object that, of course, you've heard versions of this before, but an object at rest stays at rest, and an object in motion stays in motion in a straight line at constant speed. Oh, but here it's neater on this page. So, Newton 1, unless acted on by a net external force, an object at rest stays at rest, and an object in motion stays in motion at the same speed in a straight line, or in a straight line at the same speed. Sorry, you can't read the equation. Sorry, wait, there's something in the direct chat. I'm excited. Can't read the equation. Okay, someone in direct chat saying can't read the equation. If by the equation you mean this one here, tell me. If you mean this one here, I'm going to rewrite it a bunch of times soon. It's Newton's second law, but I'll tell you what it says, if this is what you're talking about. What that says is a big sigma, a big Greek capital letter sigma, which really means sum. I think you've seen this in math before. It means sum of, sorry. So that's like a Greek letter sigma. Then it says capital F with an arrow above it. Then it says equal M times lowercase a with an arrow above it. I don't know if that, please let me know if that's what you're asking about, but you'll see it again. I mean, it's here too, if that helps at all at the top. Okay, great. All right, awesome. All right. So we'll get more to that in a minute. So that's the second law, but thank you. And more people, please. Today is definitely a day. Ask questions. I mean, my goal for today is just to give you my conceptual overview of Newton's three laws. And you've heard them before. So what you're really looking for is what new things am I saying about them? What do you need to take away about them for this class? So we're not solving a million detailed problems today. So it really is a good day, especially since hopefully you're all breathing out now, and you should be, all of you. It is a good day to stop me whenever I say something new or surprising or confusing about Newton's laws of motion. So good on you, direct chat person. And remember, you can submit for points for that. So anyway, the first law, it says it up here in white. And now I want you to note a couple of things about the first law. First of all, note the structure of it. Note the structure of the first law. What the first law is really doing is it's giving you a condition unless acted on by a net external force, that's a condition. It's saying before you go any further, this law only applies to certain cases. What cases? The cases of objects that are not being acted on by net external forces, right? That's a condition. So it narrows, okay, and I'll explain that condition in a second, but just notice that. And then it divides into two cases. It's like a tree of a trunk. No, it's not. It's like the trunk of a tree, and then the tree branches into two. And the two cases are, if you have an object that's sitting still, this is what we're predicting is going to happen. And if you have an object that happens to be already moving, already has an instantaneous non-zero velocity, this is what we predict is going to happen. So it's a condition and then two cases. That's the structure of the law. Now, what is the condition? What are the cases? Well, and please put this into notes, what I'm about to say. And remember again, anything you ever write down that I don't write down, anything you write down that I don't write down, you can screenshot and submit for points in the note-taking portal. Okay. So what I'm about to say about this is the condition, unless acted on by a net external force. I mean, it's a lot of new words there. What is it? Then you sort of know all the words, but then maybe they've never been put together in this way. So what it's really, well, like a force, I'm going to define more rigorously in a moment, but a force is some kind of influence, External means from the outside, and net means what happens after you've add up, say there's more than one of these external forces. Net means the net effect, the overall effect once you've added up all of these external forces. Okay, I'm going to be, okay. But what are these? What does that mean? Influence from the out, so we're basically saying the net effect of all the influences from the outside. What does all that mean in English? What it really means is the net effect of any influence from outside a given object really means, in the end, any influences from any other object. This is the part I want you to write down. I'm saying what a net external force really is in the end, what net external force really means in the end is the effect of any other objects on a single object. So the condition of the first law is that what we're looking at is our expectation, our baseline expectation, the natural expected state of motion of an isolated object. That's what we're saying here. The first law, the condition of the first law is we're saying, what would we expect an isolated, a single object by itself? How would we expect it to move? What is the state of motion or the future state of motion of an object if it's not interacting with any other object? That's what the first law is looking at, is isolated objects. So that really means so it means not a puck on a rug, not what happens to a puck that is being affected by a rug that's touching it from underneath, but rather maybe a puck that's on a cushion of air on an air hockey table, let's say, right? Or a puck that's on ice that is so well zambonied, so well smoothed down that the ice is barely touching it or rubbing it frictionally at all, right? Or you could say, what's the effect on like a rock in outer space? Although, of course, that was harder for Galileo and Newton to maybe directly measure, but still totally conceivable and doable to measure now in the 21st century. So what we're looking at in the first law is isolated objects that are not being influenced by other objects, okay? And what we're saying is, well, there's two cases. The case where the first object is already just sitting still, and the second case where the object happens already to be moving at some non-zero velocity. Well, what we're concluding in the first law, what we're asserting, what Newton is asserting in the first law, is he's saying, okay, let's deal with the cases one by one. One, if you just walk into the lab and you happen to be looking at a hockey puck that's sitting on an air hockey table, you walk in and you look at a hockey puck that's sitting on a air hockey table that's turned on. And I'm not saying that Galileo and Newton literally had air hockey tables, but they certainly had ice, and they certainly had the ability to smooth things down very, very effectively. So you take now to the 21st century technological extreme of that. You walk into a lab and you look at an air hockey table, and you look at a puck that's just sitting there on the air hockey table. If the puck happens to have an instantaneous velocity of 0 when you walk in, I believe most of you would expect that if nothing changes, nothing will change. Like the hockey puck will continue to sit still, right? So that's case one. Something that's already sitting still will, if it's isolated, will naturally continue to sit still. I believe that. I believe that you believe that. I believe Galileo and Newton believe that. And I believe that for thousands of years before Galileo and Newton, Aristotle and anybody else who thought about this also believed that. That case one is not such a surprise, or case A. But case B is a little bit more interesting, right? Possibly surprising. Case B says, yeah, now if you walk in and it happens that the hockey puck is already moving like to the north at 20 miles per hour along this table. If you just walk in and you don't change anything and the hockey puck hasn't yet hit the wall, and there isn't like someone's stick or paddle or whatever hitting, like if no one else is affecting the hockey puck, no other object, then what we would expect is that the hockey puck will keep doing whatever it's doing. It'll keep going at the same speed and in the same direction in a straight line. And I think you would believe that if it's a hockey puck. I believe it if it's a hockey puck. What Newton's saying is, yeah, so if we believe that about a hockey puck, like objects and motion continue, and we believe it in a meteor of outer space or whatever, we're saying like the natural state of an isolated object is that if it happens to already be moving, it will keep on moving. That's the natural state, and it's just as legitimate and true as the natural state of any object that's happening to be sitting still. Now, this is a little bit more of a pill to swallow. Like I have to keep emphasizing air hockey table here, because of course, if it's not an air hockey table, if you're watching what happens to like a hockey puck on the ground, like on a carpet, or you're visualizing what's happening to the tires of your car as they try to navigate over a rough pavement, right? In the regular everyday world, objects don't tend to be in isolation. They tend to be interacting with other objects. So what we tend to see is that without some kind of help or some kind of outside influence, things tend to seem to like they slow down, right? So much so that people like Aristotle actually believed that was a law of physics, that left to their own devices, objects will tend to slow down. But that is not the case, right? What we're saying here is no. If they're really left to their own devices, if they're really left alone, they won't slow down. They'll act the same way that the zero velocity case acts. It's only when they're interacting with other objects, like rubbing against streets or carpets or rubbing against other surfaces through an interaction that we call friction, that's when they slow down. But they need as much help slowing down as they need to speed up. That what we're saying here is either case, what ultimately, and I'm going to move on in a second, what Newton is saying here is Newton is saying, no matter what, whether your velocity happens to be zero or non-zero, what you would do naturally if you're not forced by another object, what you would do naturally is you would maintain the same velocity. If it's zero, you'll maintain zero velocity. If it's non-zero, if it's 3 miles per hour that way, you'll keep going 3 miles an hour that way. What Newton's saying is it might look like two different cases, but both cases actually come to the same thing. They come to the same idea that velocity is constant naturally. The velocity of a single isolated object is constant whether or not it's zero. Because what Newton's really saying is, I, Newton, take Galileo so seriously. I take Galileo's principle so seriously that I realize part of what Galileo's telling me is that zero is not a special velocity. Anything that's true of zero velocity has to be true of any other velocity because nothing is especially, literally, absolutely at rest. Like even an object that looks like it's going zero is only going zero relative to Earth. And Earth is going 65,000 miles an hour past the sun. And the sun is going 650,000 miles an hour past the galactic center, right? So in other words, no object is actually going zero. Zero is a matter of perspective. So anything that should be true, and so therefore no object is like trying to slow down to a speed of zero. It can't have a speed of zero except in comparison to other objects. And if it has a zero compared to one object, it doesn't have a zero compared to a different object. And we're allowed to use any objects we want as comparisons, as long as they're not accelerated, right? So if you really take Galileo seriously, what we're really saying is zero is not a special velocity. Objects are not trying to get down to zero. And if you want an object to have a non-zero velocity, you don't need gas or fuel or something. You need gas or fuel or whatever to change a velocity from zero or to zero. Nothing is special about zero. So I'm saying Newton's first law, what it really is the sixth form. It's yet a new form of this old principle of relativity. It's really saying velocity is not something that one object has in isolation. Velocity is a comparison or a relation between one object and another. And if you really believe that, you'll believe that it's just as likely, it's just as reasonable to say that objects left alone will maintain constant non-zero velocity as saying that objects left alone will maintain constant zero velocity. Okay, so that's Newton's law number one. I'm saying it's really if from now on I ever refer you to GPR form number 6, that's another way of saying Newton's first law. Newton's just picking up where Galileo left off. Okay, then we get to Newton's law number 2. This is the equation version. Okay, this is the math that someone in direct chat was asking like before. Okay, so first of all, again, to just read the symbols, that's a big sigma there, like the Greek capital letter sigma, like you use in math to mean sum of. And then it says F equals MA, but there's vector symbols over the F and the A. So what is this? Oh yeah, all right. So F net equal, so the way we read this is you either say the sum of all F's equals MA, or you say F net equals MA. Same thing. And again, you may want to take notes on this. I'm going to define a couple of terms now. I'm saying the term net external force, like here, means the same thing as sum of all external forces. The mathematical way to write net external force is sigma F, okay, with a vector symbol over the F. So in English, what this law is saying now is, okay, first law established the baseline case. First law is what you would expect of an object if it isn't being acted on by any other objects. Now we say, okay, what if it is? What happens if an object is subjected to some forces from the outside, from other objects? The answer is the object will accelerate. Again, it's just the converse of what we said a minute ago. What we said a minute ago is if you don't act on an object, if you don't force it, if you don't have a second object to somehow influence a first object, then the first object will maintain constant velocity, i.e., it will not accelerate. Now we're saying, so in fact, if you do exert net external influences on a first object, if some second and or third and or fourth, if other objects come along to interact with a first object, what they will do is change its velocity. They will accelerate it. And in fact, in a super mathematically elegant, clean, almost shockingly simple way. The greater the net, we're saying here, F net equals MA. And of course, I know you've all heard this before, but now I'm just trying to specify further. I'm saying the harder you push or pull on a mass, the greater rate at which it will accelerate. Now, acceleration, well, I'll say that again. The harder you push or pull on a mass, the greater rate at which that mass will accelerate. I'm saying F is directly proportional to A. F net, sum of F's, is directly proportional to A. The more you push or pull, the more on a thing, the more the thing will accelerate. I'm also saying that the acceleration is I'm saying also that the constant of proportionality here is M, that stands for mass, how heavy something is. So I'm also saying, if you want to put, so take that hockey puck. The more you push on that hockey puck, the more you'll accelerate it. But similarly, if you compare that hockey puck to another one, say the second one is twice as heavy as the first. If I pushed each one of them with the same amount of push, if I push just as hard on two hockey pucks, but the second one is heavier than the first one, then I'm saying that second one will accelerate at half the rate that the first one did in response to a given external force. So I'm saying net force is directly proportional to acceleration. Acceleration is inverse, and I'm saying the constant of the proportionality is mass. So similarly, acceleration is inversely proportional to mass. I don't know if that's confusing or not, or if you want, I'll just say it one more time. Net force is directly proportional to acceleration. Acceleration is inversely proportional to mass. The more you push on something, all other things being equal, the more it will accelerate. The heavier something is, all other things being equal, the less it will accelerate in response to a given force. If you want me to say that again, I will. But otherwise, I'm moving on. Just please also notice, wait. Yeah, so I'll read the English now, the yellow. It says the sum of all external forces acting on an object. Well, I'm just defining. So the left side is the sum of all external forces on the object. The M I'm defining as the inertial mass of an object. I'll be more specific about that in a moment. But basically, how heavy something is if you were to put it on an inertial balance. Um, and A is the instantaneous acceleration of that object. Now, this is the part I want to be clear about right now. M refers to the mass of an object. A refers to the acceleration of that object. F refers to all the forces acting on that object. So it's important to realize that M, the mass that we're talking about here, is the receiver of the forces. What we're saying here is the harder you push or pull on a thing, the greater the rate at which that thing will accelerate in response to the force, to the net external force. If you want to put it another way, net external force is like the cause, and acceleration is like the effect. M is the receiver of that cause and effect. It's not. So what I'm really trying to say is, there's a common misconception that if you don't already have it in your mind, I don't want to put it in your mind, but there's a common misconception that somehow this law means something like the heavier you are, the more of a force you have. It seems like it might mean bigger M's have bigger F's or something like that, or bigger M's can maybe exert bigger F's or something. I don't want to spend too much time because that's wrong, but just in case that's sort of what you were thinking, let me make clear that's wrong. Like, first of all, no object in the world has a force. A baseball does not have a force. A baseball bat does not have a force. Nothing has a force. A force, you'll see in a moment, a force is something one object does to another object. It's more like a verb than an adjective, and specifically a transitive verb. It's more like, that's an analogy, but a force is something it's an action. You do it to another object. You don't have it. So first of all, it doesn't matter how heavy you are. The heavier you are, the more mass you have. Just that, the more mass you have. And what that really means, if you're really heavy, what's the difference between a 2-kilogram object and a 1-kilogram object? The difference is that a 2-kilogram object changes to its motion more than a 1-kilogram object does. Like, that's what mass really means. It means that if I try to get the 2-kilogram object going and I try to get the 1-kilogram object going by pushing them with the same amount of force, the lighter object will get going at twice the rate, will accelerate at twice the rate than the heavier object. So the more heavy you are, the more you resist acceleration, the more you resist the effect of net external forces, the harder it is to get you to accelerate. That's what it means to be heavy. But what we're not saying is that heavier things push harder or something. That's not what this law is saying. Maybe sometimes that's true, but that's not a law. We are saying when you push an object, it accelerates. And the more you push, the more it'll accelerate. The heavier it is, the less it'll accelerate, like all other things being equal. So the mass in question here is the thing receiving forces and then accelerating in response to those forces. Okay, I'm just trying to clear up a misconception. Okay, so that's what in short, this law means, again, I'm just trying to give an overview right now, but yes, this is the law that ultimately is used the most directly and explicitly for problem solving in physics for the rest of time in physics. So another thing to note about this law is that it's a vector equation. Notice I'm putting arrows above the F and the A. F, force, is a vector. A, instantaneous acceleration, is a vector. Now, we've been spending all of the time in the course up until now dealing with acceleration in vectors. I mean, that's basically what the whole midterm was about, was acceleration in vectors. So what's the takeaway there? Well, first of all, by A, we mean instantaneous acceleration. The rate at which you change your velocity at a moment, like the second derivative of position with respect to time. Anything we believed about instantaneous acceleration in all the equations that you just got tested on, that's what we mean here. But furthermore, anything that we believe about vectors, we mean here. So remember GPR, Galileo's principle of relativity, form number 5. Remember, well, I'll just say it in the context of this. This is a vector equation, F net equals ma. So what we're really saying is if you're in three-dimensional space, like the world, this is really 3 equations occurring simultaneously but independently. To say F net equals ma is really to say along a given axis, you add up all the forces acting on that given axis on an object, and you will find out the rate at which that object will accelerate along that given axis. Along x-axis, Newton's second law is true, while at the same time, but utterly independently, along the y-axis, Newton's law is true. And then again, like simultaneously and independently along the whatever axis, I don't even remember what that z-axis, it's also true. So it's really 3, and you'll see this in problem, it's really 3 separate equations happening without affecting each other, but all at the same time. Last point on this, and then I'll move on. They're vectors. So on each axis, like you could have a bunch of pushes or pulls happening this way and a bunch of pushes or pulls happening that way, acting on any given object on a given axis. On a given axis, we distinguish one direction from the other with minus signs, right? So what we're really saying here is, and I think, is this what I wrote on it? Yeah, okay, so here we go. Well, the next bit, this is just notes about the same equation. Notice, first of all, this equation is really 3 equations happening simultaneously yet independently. That's what it says. Fx, Fy, Fz equals max, may, maz. But second of all, you got to take into account minus signs. That's like, you've got to take into account minus signs, meaning, and this is where sum of and net mean the same thing. Like, if you look at some object and you look at the x-axis, what's happening on the x-axis? Say on the x-axis, you have 5 units of force pushing to the east, while you also have 2 units of force pulling to the west, let's say. Then by net force, by sum of the forces, we mean add up on that axis, add up all the eastern directed forces, add them together with the western directed forces, but add them like we always add vector components. Take into account the minus signs. So if you call east positive and you call west negative, then you have like positive 3 plus, you have like positive 5 plus a negative 3, or whatever numbers I just said. So then if you're doing it properly, it'll end up sort of looking like subtraction. It'll be 5 plus negative 3. So the net effect is 2 in the eastern direction. So sum of all forces, F net, as a vector, really means add up all the positives going one way and take away all the negatives moving the other way. And that will give you the net force on a given axis. And divide by the mass, and you'll have the acceleration along that axis. Do that separately for each axis, and you've now applied Newton's laws, or Newton's second law. How do we know all the forces acting on an object in various plus and minus directions and on various axes? Ultimately, what we do to figure out all the forces acting on an object is we draw diagrams called system schemas first and free body diagrams second. That's ultimately what the homework gets into. And you may have to do a little research on the web to get a little preliminary on that because I won't be able to get into it today. And or that's what you could totally talk about with Professor Liu on Wednesday. But you draw pictures in order to figure out the net force acting on an object, to figure out all the arrow vectors acting on an object, and then you add them all up on each axis simultaneously, separately, in order to get the acceleration on each axis. That's how it works. So the main focus first that we need to learn is how to draw these diagrams. That will happen. You'll do your best attempt to research that on Google or whatever, or Khan Academy, whatever, tonight and tomorrow, and you'll make a first attempt to see what you figured out on your own, and then you'll talk about it more with Professor Liu on Wednesday. And then if you got anything in that was at all authentic, you'll be able to get all the rest of the points later. Okay, anyway, so that's one note, that Newton's second law is a vector equation and involves pluses and minus signs. The second note is units. Mass is always measured in kilograms. Acceleration, as you know from all our prior work, is measured in meters per second squared. So a unit of mass times a unit of acceleration gives you a unit of force, according to this equation. So from now on, a unit of force is known as a Newton. I mean, it's an SI, it's a MKS metric unit. A Newton of force is by definition equal to a kilogram of mass times a meter per second squared of acceleration from now on, okay? So those are just notes on Newton's second law. Now, and again, stop me. Now Newton's third law. Okay, bear with me for a second. Newton's second law, Newton's third law. You might find the English here a little bit clunky. I assure you that it is not by accident. Oh no, okay. It's not by accident, and it's sorry, I noticed a couple of new things in the chat. Okay, there's just a couple things in the direct chat, and please do keep the chat. I know I'm just talking and talking and talking, which is not necessarily relaxing. Hold on, just. And there's like no video, so it's hard to tell where you. All right. Well, all right. I'm gonna pause for a second. Can you? I mean, I want to do Newton's third law now, but just give me an electronic hand if you're still with me at all. Like, are you? I mean, I know you're probably exhausted, many of you, but yeah, okay. Thank you. Thank you, Gabriella. Thank you, Sydney. Thank you, Kaya. Thank you, Genesis. Thank you, Brandon. Thank you, Ariana. Thank you, Erica. Thank you, Roger. Thank you, Samantha. Thank you. Okay. And I think there were a couple others and then it went bad. Thank you, Andre. And thank you, Matthew. Awesome. All right. That's a quorum. Okay. Thank you, Joran. Joran. Okay. So I'll keep going. But again, you feel okay. I'll just keep going. Oh, yeah. So Newton's third law. I'm using a lot of words here. You might they're not unnecessary though. I mean, they're conscious choice. And oh wait, and Joran, sorry, or Joran, is your hand up for a question, or are you just raising? I mean, thank you for raising your hand when I just asked a second, but you could put it down now unless you have a question. Feel free. Okay. I mean, you're good, Joran. Yes. Okay. Well, oh yeah, no, that's fine. It's fine, no problem. And I can. Oh, it's stuck. Okay, good to know. No, fine. That's totally. No, at least look, that totally shows you're alive. I mean, you're very alive, which is really my biggest concern. Hold on, I'll lower hand. Okay, okay. Oh yeah. All right. This third law you may have heard. Look, you've heard all these laws before. I know that. But I'm trying to unpack them more at a higher level. So this third law you may have heard throughout your life as as for a reaction, there's an equal and opposite reaction. I mean, this is that law. Yes, the third law is the action reaction law, if you've ever heard about it before. But I'll tell you right now, it's definitely the most easily misunderstood of the three laws. It's a very important law, and it's very easily misunderstood, and it's very easily misapplied. And it's important to do physics to apply it correctly. So the first thing I want to say is, yes, it's the action reaction law, but that is a deceptive, confusing way. Like I would start thinking of it this way if I were you. And what is this way? The way I'm writing it is when or whenever, when object A exerts a force onto object B, that object B exerts a force onto object A of identical magnitude and in opposite direction. Let me break that down a little bit. First of all, A and B are just arbitrary objects, like we used before with velocities and stuff. A and B just mean any two random objects. Notice, first of all, the main purpose of what I'm saying here is I'm trying to direct your attention to the fact that we need two objects to even talk about any of these forces at all. So if you have two objects, if one object exerts a force on the other, what we're saying here is that automatically the other exerts a force on the one. And in fact, specifically, it exerts a force on the one of the exact same amount, the same strength, the same number of newtons, but just in the opposite direction. So what we're really saying here, and this is when you really start in like everything in physics, when you first hear it, maybe it sounds obvious, or like it sounds like a bunch of words that are unnecessary to capture such an obvious idea. But the more you think about it, the more you try to apply it or whatever, the more it may not be obvious at all. In fact, it is not. So to be more specific here, notes. Oh, in fact, let me just, sorry, I just want to see. Oh yeah, okay. So notes on this. Oh, and good afternoon, people who just. Oh no, okay. What notes on this law? First of all, in super simple English, what I'm saying is if I push you, you push me back. If I push you, you push me back. And in the exact same way, if I push you with 3 newtons of force, I don't care what it looks like. It may not look, you'll see why in a minute, it may not look like this, but if I push you with 3 newtons of force, you push me with 3 newtons of force in the opposite direction. And that's what, by the way, and you might want to put this in your notes, pushing means away from, pulling means toward. So if I push you to the north, if I push you away from me with 3 newtons of force directed to the north, you necessarily push on me with 3 newtons to the south. And I'm not saying because you make a decision to get revenge. Like, we don't have to be human beings. In fact, we shouldn't be human beings for this even to be clear and true and vivid. Let's say I'm a billiard ball and I smash into you, right? If I hit you and so I'm pushing you 3 newtons to the north, you are automatically, necessarily pushing me to the south, definitely. Second of all, it's simultaneous. It's not actually a cause-effect thing. It's not a cause effect. It's not act and revenge. It's so simultaneous that, in fact, it's a matter of perspective. It doesn't matter whether I think I'm the one pushing on you. Like, it's just a matter of perspective, which one you think of as the action and which one you think of as the reaction, which is part of the reason I don't like that language. There's other reasons too. But like, it's not like either one can be thought of as, it's just two actions. Really what it is two sides of the same one action coin. What we're really saying, so note number 3, what we're really doing here in the law number 3, and why I wanted to get to it before saying any more about law 1 or law 2, here in law 3 is really the working definition of a force. Here's what we're really saying is from here on in, when we talk about forces, when we talk about external forces, what we're really talking about is interactions with other objects. What we're really saying from now on is a force is an interaction between two objects, between two masses. A force is one mass interacting with another mass. And that is the best word to use for it in physics. In physics, if you want the best possible synonym for force, it is interaction. And if you want an English informal word for interaction, there's 2 choices, push and pull. And what I am literally saying is every interaction in physics, every force in physics is either a push or it is a pull. It's one or the other, and it's not both, and it's not neither. So I'm literally saying, and pushes and pulls, we're saying are symmetric. If I push you this hard, then you push me this hard. If I pull you this hard, then you pull me this hard. A push is a symmetric interaction between two objects. Even when, let's say, I push against the wall. If I push against the wall with 5 newtons of force, you might say, well, the wall doesn't push you back. I mean, that's ludicrous. Like, what? Like, or, I mean, clearly something different happens to you from what happens to the wall if you push the wall with 3 newtons. Let's think about it. Think about this law in connection with the second law at the same time. if I push a wall with 3 newtons of force, first of all, I absolutely believe the wall pushes me back. Why do I believe that? Well, first of all, my hands hurt. I mean, I could feel it in my hands. If I were literally just pushing the wall and nothing were happening to me, there's no reason my hands would feel anything. So I push the wall, it automatically pushes me back. And in fact, if I push the wall hard enough, I start accelerating back, right? Like say I'm running into a wall. I'm running into a wall. I'm going at some high speed, some high velocity. I start interacting with the wall. I start touching the wall. First thing that happens is I accelerate the other way. I accelerate, like I'm going this way into the wall. The wall pushes me the other way, so it accelerates me the other way. What's the evidence of that? I slow down. I'm like big old duck, right? I have a velocity pointing positively. The wall starts exerting a force on me the opposite way. So it starts giving me negative acceleration. In other words, F net equals ma. F can be positive or negative. A can be positive or negative. We're not saying that forces only speed things up. Forces change velocities. They can speed up, slow down, or they could change direction, or some combination of the two. So if I run into a wall, the wall starts to decelerate me. I'm in contact with the wall long enough, I like smash into the wall. But if I'm a rubber ball or something like that, you'll eventually see me now pop out and go the other way, right? So the wall has decelerated me so much, it sends me into negative velocities and I fly out from the wall, right? Now, then you might say, but wait a second, the rubber ball that's going into the wall, or the human being, whatever, that goes into the wall, like now it moves a lot the other way, or it accelerates a lot the other way. The wall doesn't seem to experience any effect. So what's going on? How can you say that it's the same numbers both ways? I'm saying it's the same force both ways, but F net equals ma. If you exert the same force on two objects and one of them is heavy and one of them is light, one of them is very massive and one of them is not very massive, then the more massive one accelerates less. So I go into the wall, I'm pushing it with 3 newtons of force. That accelerates this huge, enormous, massive wall a tiny bit. How do we know that it accelerates it at all? Well, if I'm heavy enough, I make a dent in the wall, don't I? So that means the outer edge of the wall starts accelerating in towards the center of the wall. That's called a dent. So you absolutely do accelerate the wall, but just a little bit because you exerted a given force and the whole thing has a big M. So its A is small, but then me compared to the wall, or the rubber ball compared to the wall, receives that same force, but now it's that same force exerted on a tiny m, so it gets a big A. You understand? So I'm saying forces are always mutual between two objects. Accelerations are not. Accelerations are dictated by F. Acceleration is the consequence of the effect of force. Law number 2. What is a force? Understand it through law number 3 and I know we have 4 minutes left. A force is a mutual or symmetric interaction between two objects. Why are the numbers the same? How can you say if I push you, you push me back the exact same way? Because how much you push in the first place is a matter of perspective. Who you look at as the pusher or the pushee is a matter of perspective. Oh, where'd it go? Oh yeah, look to the side of this in red. I'm saying that really, law number 3 is ultimately the definition of force. A force is an interaction between two objects. Just like Galileo's principle of relativity said, a velocity is a relation between two objects. You can't have a meaningful velocity if you just have one object. You can't have a meaningful force if you just have one object. A force is, and just like with velocities, VAB equals negative VBA. Forces work the same way. FAB equals negative FBA. This is just the 7th form now of Galileo's principle of relativity. The 6th form was the first law. The second law is just a mathematical encapsulation of both of these ideas. The 5th form was the X and Y axes thing. The 4th form was the 1 object, 2 object, 3 object case, et cetera, et cetera. I'm saying here with 3 minutes left, I'm saying a force is just is one object affecting the other, and one object cannot affect the other without the other affecting the one. It's the same way in an opposite direction. It's literally like saying, I married my wife on October 20th, 2012, right? I married, my wedding anniversary, I'm not trying to get personal, I'm just using this as an example. My wedding anniversary is October 20th. 2012, you want to hear a crazy coincidence? Check this out. It happens of all the people for me to marry. Imagine this. The woman that I chose to marry on October 20th, 2012, you know what we have in common? She has the same wedding anniversary date. She also got married on October 20th, 2012, only to me. Like, I am trying to be a little silly, but think about that. Oh, thank you. Someone react, thank you. But like, literally, I'm saying forces are the same way. It's the reason that's like funny, even if it's not funny, is that, of course, like, duh, right? Like, obviously, I married my wife the same day that my wife married me. Only the difference is I married her. And from her point of view, she married me, right? Or God, God love her, like whatever, right? Same thing with forces. From my perspective, I pushed you, but from your perspective, you pushed me. And of course, in the same way, it has to be on the same. I married my wife on the same date. She married me. If you push me 3 newtons of force, I push you with 3 newtons of force. It's just a matter of how you look at it. It's GPR number 7. So we're like 30 seconds early for a small change. I'm going to end on that. So that's just the overview of the 3 laws. It's just a new way of looking at Galileo's principle of relativity. Again, the more you can get your mind around Galileo's principle of relativity, the more all of physics, each new topic just opens up and opens up. They're all just further, more detailed implications of this same idea that we're looking at objects in relation to each other, not in isolation. Now, I'm done. Have a very nice day. If for whatever reason you need to have a conversation with me or you need to give me an exam or whatever, hang out for a minute. I'm going to make breakout rooms. But everybody else, have a nice and stop. Or also, if you want to just hang out for a second and ask a question, that's fine too.